So, in this lecture, we are going to discuss our pseudo-rapidity results in proton-proton collision. As you know, in previous lecture, we discussed about the multiplicity results in pp collision. So today we'll discuss about the second results, which is the pseudo-rapidity results in pp collision. Similarly, we are using the same energies, like we are using the lowest energy of pp, which is 0.9 TeV, the middle energy, which is 7 TeV, and the max energy yet achieved in proton-proton collision, we are taking 13 tera electron volts. Okay, so we are checking the pseudo rapidity results. Along with that, we are setting jet variations, like we set it value jet as on, and then we set our jet off. Similarly, we will check the results when setting the value of jet as 1. So let's just start it or the results for this pseudo rapidity of proton-proton collision. So for that, so let's start, uh, as we will first discuss the general shape of the distribution of these curves, the general shape, what it shows. Okay, so as you can see, the distributions are approximately symmetric. Okay, at eta equals to 0. You can see this is the pseudo rapidity on the x-axis, and along the y-axis is this, and so on x-axis basically the distribution of pseudo rapidity. You can see the distributions of all energies are symmetric at eta equals to 0. What is eta? It's the pseudo rapidity, and when your eta is 0, and when is your angle is 90 degree. Okay, the angle between the beam axis when is perpendicular, so this is so called as when your eta is at 0. Okay, so eta is, you can see, is symmetric with the peaks, you can see, near 0. What it indicates, it basically indicates that higher density particles produced at the central region. Okay, because you can see the only density of these particles shows a peak behavior at eta equals to 0. Then there is a rapid decrease, means density of particles now becoming decrease once you increase the value of eta, either in the forward direction or either in the backward direction. If you increase the value of eta, so you can see, means the your peak shift towards the lower densities. Okay, so these distributions are approximately symmetric. You can see, beyond 0 and before 0 is same. Okay, curve, so you can say that's why symmetric around eta equals to 0. And it indicates that, you can see, it indicates that higher density particles produced in the central region. Understood? Ours now just discuss another distribution of general shape, is that the density of particles decrease. As I mentioned, you can see the density of the particles decreases, okay, with an increase in mod of eta. So as you increase the value of eta, either in forward direction, because this is mod of eta, and if you are decreasing the eta means negative, so because mod, so it become positive. So either if you increasing the value of eta in forward direction or in the backward direction, what you will get, the density of the particles got decrease, okay, by increasing mod of eta. Corresponding, what it corresponds that to fewer particles being produced in the forward and backward direction. In the forward and backward direction, only fewer particles are produced, while at the central region, the most and the high density particle produced, while in the forward and in the backward direction, you can say that a fewer particles being produced, okay, relative to the beam axis. So that's the results for the journal shape. You can by checking these graphs. So journal shape discussion is this. Now let's check the by variation in energies, because you know that we are having three energies at zero point 0.9 TeV, 7 and 13 TeV. So we have to check at different energies. As you can see the graphs, as collision energy increases from zero point 0.9 to 13 TeV, the height of the central peak rises. You can see here is the height is 3, this is at 2.5, and this is at 1. Similarly, this changes up to 1.5, and this up to 3, 2.5 converting to 3, and this peak at now 5, which is previously at 3, now it becomes at 5. Similarly, when you increase the most energy at 13 TeV, you can see the peak after 5 goes to 6, and this peak after 3 goes to 3.5, and this peak after 1.5 goes to 2. So the peaks, you can conclude that by as the collision energy, when you increase from zero point 0.9 to 7 to 13, the height of the central peaks increases, rises. Okay, so what it suggests, greater particle produced at higher energies. Here less number of particles produced, here more less, here greater, here most greater number of particles produced at the higher energies, because you can see the it shows a peak, the most central peak rise at 13 TeV energy. Understood? Okay. So now let's compare the jet dependence comparison of our data by jet variation. So we are setting our jet as on JD. Here your black distribution shows when your jet is set as on, and while your red curve, these circles, shows when your jet value is set as off, and these triangles, blue color shaped, tells us about when you set your jet as value 1, and this is similar for all other energies in 70 ev or 13 TeV. Okay, so let's check the jet dependence. As you can see, the JD data shows the highest peak density. You can see JD, this black squares, shows the highest density other than this blue, other than this red curves. In all these different energies, only the black distribution shows the highest particle density across all pseudo-rapidities, okay, ranges. Then it followed by J1, then J0. Similarly, J1, J0. Then it followed by J1, J0. So it remains constant for all the three different energies, like as you can see the JD distribution shows the highest particle density, means when you set your value of jet as on, then you will get the maximum highest particle density. Understood? Then this blue triangle shows the intermediate behavior, then followed by J0 when you're set as Z off. Okay, so these results are coming, and now let's check. And the next thing is that this order remains this order. Which order? Like JD is the most dense particles production, then followed by blue, then red. Similar in this case, similar in this case. So you can say that this ordering suggests that JD events contains more overall activity. Understood? Why more activity? Because here highest particles density, okay, at JD, while J0 are relatively low because it has the lowest particle density. Okay, so lowest particle density when your jet is off, and when your jet is on, you will achieve the highest particle densities. Also, by increasing the energies, the peak got rises, means higher density particles produced. By increasing the amount of energy and by setting your jet as on, you can easily achieve the high density particles. Okay, so now let's finally check the implications for understanding particle production in this case. Okay, so because we are concerning with the pseudo-rapidity results in proton-proton collision, so you can say that the first implication is the pseudo-rapidity distribution can be used to validate the theoretical model of particles production. Okay, but particularly at the central region, because you can see that only at the central region your pseudo rapidity, or you can say that the distribution are approximately symmetric at eta equals to 0. So particularly in the central region, the central rapidity region, the pseudo rapidity or the distribution is symmetric. So that's why this pseudo rapidity distribution can be easily used to validate the theoretical model of particle production only at the central region. You know that in the forward and in the backward region there is less broader, and you can see that as the density of the particle decreases, while when you go in the forward and in the backward direction. Okay, not going in the forward direction, you can see there is a decrease in the density of the particle, and if you go in the backward direction again, there is a decrease in the particle production. Okay, similar case here and similar case here. Our second amplification is that this results basically highlights how collision energy im- how collision energy influences the spatial distribution of particles production. Understood? These results basically are highlighting how these collisions, influences the spatial distribution of particle production, which is very very important for understanding the dynamics of proton-proton collision. So that's why the distribution of pseudo rapidities are very crucial. Understood? Because it highlights how collision energy influences, means by changing the amount of energies, by changing at different energies, we can easily influence the spatial distribution of these particle production, and which is very important to basically understand the dynamics of proton-proton collision. Okay, so that's all for this lecture of our results of pseudo-rapidity in proton-proton collision at three different energies, 0.90 eV, then 7, and at 13 tera-electron volts. Then we check the jet dependence by setting our jet as on, then jet is off, J0, and setting as jet J equals to 1, which shows the intermediate behavior in all these curves. So that's all for today. In next lecture, we will discuss the transverse momentum distribution in proton-proton collision. Till then, stay tuned with us. Take care and Allah Hafiz.